Recording. We're just continuing 12.5.
Planes, yeah. Okay.
So last class we started talking about planes. And we said that every plane can be determined by two pieces of information, kind of similarly to lines in R2. The first piece of information that we need is some point that the plane passes through, and we will call that point P0. And the second piece of information that we need is a vector that is normal to the plane, and we call that the normal vector. And this is a vector that is orthogonal or perpendicular to all the vectors that lie in the plane. And so then we can draw our plane like this. Here's our plane. And this would be the point P0. And this would be the normal vector to the plane. So that's the vector n. And we saw that the equation for a plane is written by ax plus by plus cz is equal to d. And you can read out the information for the normal vector through this equation by looking at the coefficients in front of the x, y, and z. So our normal vector is a, b, c in this case. And so an example would be if I tell you that your normal vector is equal to 1, 2, 3, and your plane passes through the point 1, 0, 1. In order to find the equation of the plane, you write out x plus 2y plus 3z is equal to d. So we have almost all the information that we need for this plane. Now, in order to find d, you plug in your point. So you go 1 plus 0 plus 3 is equal to d. In other words, d is equal to 4. So the equation of our plane is x plus 2y plus 3z is equal to 4. And that would be the equation of this plane. Any questions about this? Okay. Now, the reason we get this equation can be thought of as something like this. If we are really looking at a normal vector, n, and we say by being normal, we mean that it is perpendicular to all the vectors that lie in the plane. So let's take some vector that lies in the plane. And this vector starts from this point, which is the point P0, and we'll write it out as x0, y0, and z0. What we are saying is that the normal vector, so here's our normal vector A, B, C. When I take my normal vector and I dot it with any vector in the plane. So what does a vector in the plane look like? So let's say this is a vector in the plane. It's a vector that starts from this point and ends up at a point x, y, z in the plane. So here's a point x, y, z in the plane. Or in other words, it's the vector. So this is the vector in the plane, and that vector is going to be x minus x0, y minus y0, and z minus z0. So this is a vector in the plane. It's actually the set of all the vectors in the plane. Starting, so by definition, we're assuming that this is the set of all vectors in the plane. The x, y, and the z vary, and it's the points that start from this point over here. So it's, let's say, this vector, this vector, this vector. Any questions about this? So how do we describe this fact? Well, we can say that if I take my normal vector and I dot it with this vector, which is by definition the vectors that lie in the plane, so I dot it with x minus x0, y minus y0, and z minus z0. What should I get when I take the dot product between these? Yeah, 0. So you get 0 because we're dealing okay, we're dealing with all the vectors which are orthogonal to n. So if I take n and I dot it with these vectors, I get 0. So if I write this out, I get a, b, c, which is my normal vector, dotted with x minus x0, y minus y0, and z minus z0 equals 0. Any questions so far? Okay, so let's write this out. This tells me a, x minus x0 plus b, y minus y0 plus c, z minus z0 is equal to 0. And now if I write this out, what I get is ax minus ax0 plus by minus by0 plus cz minus cz0 is equal to 0. And then what we can do is we can say ax plus by plus cz is equal, so that was this, and that. And I move the coefficients to the other side. So I get ax0 plus by0 plus cz0. And this is just a constant. ax0, by0, cz0 is just a constant. So we can say ax plus by plus cz is equal to d. And that's how we get the equation for our plane. So by definition, what this equation is saying is all the points, all the vectors that are orthogonal to the vector ABC, right? This is a vector. And when we say when you dot it with ABC and you get 0, that is the set of all vectors that are orthogonal to ABC, and that's a plane. Any questions? So that's what you see over here. That's this computation. And so then you get the equation for the plane. And the equation in vector form is the normal vector dotted with x, y, z is equal to that d, that coefficient that we put on the other side. And the equation in scalar form is this, the equation that we've been seeing. And what is d? D is just ax0 plus by0 plus cz0. But if you want to find d, there isn't any reason to memorize that formula. All you really need to know is you need to know this formula, You need to know what the A, B, and C stand for. They're your normal vectors. And then if someone gives you a point in the plane, you just plug that in to X, Y, and Z, and that will tell you D. So that's basically the information that you need. You need to know how to find the normal vector and how to plug a point in to this equation to find D. Okay, so they give us an example. Find an equation of the plane through the point 3, 1, 0. So P0 is equal to 3, 1, 0. And our normal vector is 3, 2, negative 5. So 3, 2, negative 5. So please take a couple of minutes and do this problem. Okay, so let's do it. So again, we're looking at the equation AX plus BY plus CZ is equal to D. So that tells us 3x plus 2y minus 5z is equal to D. Then we plug in our point P0 and we get 9 plus 2 plus 0 is equal to D, which is equal to 11. So we get 3x plus 2y minus 5z is equal to 11. Any questions? Yep. Yep.
So we don't always start with the normal vector, because we've been doing that for the other questions. So, I started with the normal vector of our 3x plus y.
3x plus y. I mean, you put the normal vector, you're given the normal vector here. So you put it in front of the A, B, and C. So this A comes directly from here, that's 3. And then this B over here comes directly from this 2. You put it in front of the Y.
Oh, never mind.
Any other questions? Okay. So the next example that they tell us is we have an equation of a plane and we want to find an equation of the plane that's parallel through it. And the first one says it passes through the origin, and the second one says it passes through this point Q. So let's write this 7x minus 4y, 7x minus 4y plus 2z is equal to negative 10 plus 2z is equal to negative 10. Okay, and origin and Q2 negative 1, 3, 2, -1 and 3. So can anyone give me some idea for how to go about doing this? Yes,
I'll use that as the point of the plane since the parallel is the same normal vector.
perfect. And similarly with the origin. So we can say, okay, my normal vector now is equal to 7, -4, and 2. And any plane that's parallel to this plane, any plane that's parallel to this plane right here, will have the same normal vector, just going through a different point. So to start with, let's do the first one, A, which is going through the origin. Well, we know that my plane has the form 7x minus 4y plus 2z is equal to d. In order to find d, I just plug in the origin 0, 0, 0. So what would d be? 0. So I get that the plane has the form 7x minus 4y plus 2z is equal to 0. Okay. For the next one with Q, what we can do is we can plug in Q. So we can say 7 times 2 minus 4 times -1 plus 6 is equal to my d. So that's 14 plus 4 plus 6, which is 24. And so that's my d. So now I just write 7x minus 4y plus 2z is equal to 24. Okay, so the first answer is this one over here with 0 for d, and the second one is this one over here with 24 for d. Any questions? Okay. So here's a nice picture representing what we just discussed, which is all these planes are parallel to each other. So they all have the same normal vector, 7, -2, -4, and 2. But they just have different d's. So they're just, it's actually, okay, in this picture, it's easier to see that they're parallel. Okay, I guess, yeah, they're parallel. So anyway, this one is the one that passes through the origin. This one over here is a little lower because you have a -10 for your d, and that one over there is a bit higher. Okay, on to the next situation that we want to deal with. Let's imagine that we don't know the normal vector, but we know 3 points in the plane, P, Q, and R. Now, if you only have 2 points, there isn't a plane that's defined by only 2 points, because for 2 points, you can rotate and be inside of the 2 points. For example, so let's say I give you 2 points and I say, find the plane, the path that contains these 2 points. There isn't just one plane. You can have this plane. You can have this plane over here, but you can also rotate the plane and maybe have something that looks like this. And we can imagine it still contains the 2 points. A line is described by 2 points, like we talked about, and you get the equation of your line. But a plane needs 3 points to be described. But if you have 3 points, there's only one plane that will contain all 3 of these points. And the question that we might want to know is how to find that plane. So let's say I give you 3 points, P, Q, and R. Can anyone tell me a strategy for how to find the plane that goes through these 3 points? Yeah. So draw a vector from P to Q, P to Q, and P to R. So the first vector we're going to call PQ, and the second vector we're going to call PR. Yeah, continue. Take their cross product. So the normal vector to our plane will be the vector PQ cross PR. So now we have our normal vector, and we then need one point in the plane. We have three. We can choose one of them, and we will be done. Any questions about this? Okay. So that's this picture over here that you see. You're given 3 points, P, Q, and R. You get the normal vector, PQ cross PR. And so here's an example. So find the equation of the plane determined by the points P, 1, 0, negative 1. So P is the point 1, 0, negative 1. Q is the point 2, 2, 1, 2, 2, 1. And R is the point 4, 1, 2, 4, 1, 2. Okay, so step one, let's find the vectors PQ and PR. And try not to get confused and take the cross product of these points or something like that. We need actual vectors. So let me draw a diagram so that we see the different steps. So we have these 3 points, P, Q, and R. So the first step is to find the vector PQ. So the vector PQ is equal to 4 minus 1, 2 minus 1, which is 1, 2 minus 0, which is 0, and 1 minus minus 1, which is 2. The vector PR is equal to 4 minus 1, which is 3, 1 minus 0, which is 1, and 2 minus minus 1, which is 3. So 1, 2, 2, and 3, 1, 3. Let's make sure 1, 2, 2, 3, 1, 3. Perfect. Okay, now the cross product. So we can say our normal vector is the vector PQ cross PR. And we make our matrix I, J, K. And we put in our first vector PQ, 1, 2, 2, and our second one, 3, 1, 3. And so now taking the cross product, we get I times 6 minus 2 minus J times 3 minus 6 plus K times 1 minus 6. That gives us the vector 4. 3 minus 6 is negative 3, so we get 3. And negative 5. 4, 3, negative 5. 4, 3, negative 5. Perfect. So now we have our normal vector. So we can say my normal vector is the vector 4, 3, negative 5. Any questions so far? So then my plane has the form 4x plus 3y minus 5z is equal to d. Now I only need to find d. So I can go back, find the point P, 1, 0, -1. And you can use any one of the 3 points. So my point P was the point 1, 0, -1. So I plug that in, I get 4 plus 0 plus 5 is equal to D. So now I know that 4x plus 3y minus 5z is equal to 9. And that should be the equation of my plane. Okay, so in order to verify that this equation contains our 3 points, let's take the point Q, which is the point 2, 2, 1, 2, 2, 1. Two, 2, 1. Plug it in. So 8 plus 6 minus 5. What? Yeah, 8. Okay, so this is a 9, right? Yeah. What about the point R? And so this is correct. We plug Q in here and we get 9. What about the point R? And if there's a good way to verify that what you did is correct, I always recommend that you do it. There's no reason why not. 4, 1, 2. 4, 1, 2. 4, 1, 2. So this tells us 16 plus 3 minus 10. So that's 6 plus 3, and that's also 9. Any questions about this? So that is how to take 3 points and find a plane. Yeah.
So this means that after I get my normal vector, I can like substitute
Yes, yeah. And you'll get some number for D, and then that's your equation, and then just verify it with the other points to make sure it's correct. And we see that it's correct, that each one of these points satisfies that equation, so it lies in the plane. And of course, there are other points. So for example, the point 0, 0, 3, 0 also lies in this plane. Okay, any other questions? Okay. So before we continue, let me ask you to find the plane that goes through the points P is equal to 1, 0, 1. Q is equal to 2, 0, 0. And R is equal to 3, 1, 1.
So put it up here, I mean, computer thing is not a or yeah, or you can or you can put it oh yeah, my bad. Yeah, the equation of the in this equation, since it's x, y, and z, it's like dot product. X, y, and z, you put in your point, and whatever you keep that, that's whatever. But it's like, so that's the normal vector A, B, and C. And the other one, so then it's like
Okay, so let's do this problem. So first we need to find the vector between P and Q. So the vector between P and Q, 2 minus 1 is 1. 0 minus 0 is 0. 0 minus 1 is negative 1. The vector between P and R, so 3 minus 1 is 2. 1 minus 0 is 1. And 1 minus 1 is 0. So far, are we good? Yeah. Okay. So now our normal vector is equal to the cross product of PQ cross PR. And that's equal to the determinant of the matrix I, J, K, 1, 0, negative 1, 2, 1, 0, which is equal to I times 0, and then 1 times negative 1 is negative 1, but then you put a negative, so you have a plus 1, minus J times 0, and then again 2 times negative 1 is negative 2, but then you have a minus, so plus 2, plus K times 1. And that's equal to 1, negative 2, and 1. So far, is this correct? Yep. Okay. So now let's take the equation of our plane and get x minus 2y plus z is equal to d. Take our point P, which is, or the point Q, 2, 0, 0. So that tells us that d is 2. So we get x minus 2y plus z is equal to 2. Any questions about this? Okay, so next problem. So now that we know what a plane is, and we also know what a line is, we can try to find the intersection of planes and lines. So if here's my plane, here's a line, and the plane is written in the equation. Okay, let me go to a different board. Okay. So here's my plane. Here's my line. The equation of the plane is ax plus by plus cz is equal to d, and the equation of the line is rt is equal to r0 plus tv. And we want to know, where does this plane and this line intersect? Okay, can anyone give me some technique for how to figure out where this plane and this line will intersect? So what we can do is we can rewrite the equation of the line in terms of x of t is equal to x0 plus t times, so we're going to take v to be okay, let's say v1, v2, and v3. So t times v1, y of t is equal to y0 plus t times v2, and z of t to be equal to z0 plus t of v3. And now, if these two intersect, what that in essence means is if I take this equation and for my x, I plug in x of t. So I get a times x0 plus tv1. That's what I put in here, plus b. And for my y, I put in y0 plus tv2. And for my z, I put in the z part, z of t, or, okay, sorry, c times z of t, which is z0, plus tv3. And I set this equal to d, right? Because they need to be equal. That's what it means for this point on the line to intersect with the plane, that if I plug it into the plane, I get d. Well, now the only real variable that I have, I know what x0 is, v1. I only have t. The t is my only variable, so I can solve this equation. I can solve for t. And once I solve for t, if I want to find the point of intersection, so if I get t, what can I do to find this actual point? Anyone? Yes. Plug it back into these equations, into r of t. Yep. Okay. Any questions about this? So let's do a problem. So they say find the point P where the plane x3 minus 9y plus 2z, 3x minus 9y plus 2z is equal to 7. And the line is given in the form r of t is equal to 1, 2, 1. R of t is equal to 1, 2, 1 plus t of negative 2, 0, 1. Negative 2, 0, 1. So these are my two equations. Then the question becomes, where do these intersect? So let's first write out for my line, what is x of t? X of t is 1 plus minus 2t. Y of t is equal to 2, and just 2. And z of t is equal to 1 plus t. So now the next step, in order to figure out where these intersect, is to plug that into my plane. So that tells me that 3 times 1 minus 2t minus 0. Oh, sorry, 1 second. Minus 18 plus 2 times 1 plus t is equal to 7. In other words, 3 minus 6t minus 18 plus 2 plus 2t is equal to 7. So now in order to solve for t, I can just say negative 4t is equal to 7 minus 3, which is 4, plus minus 2, which is 2, plus 18, which is 20. Or in other words, t is equal to negative 5. Let's make sure. Yep, t is equal to negative 5. So then the last step, once we know t, you can't just say, oh, t, that's where they intersect. T is just a parameter. It's not a point in R3. But I can take this t and I can plug it back into these equations. And I can get, okay, x of negative 5 is equal to 1 plus 10, which is 11. Y of negative 5 is equal to 2. And z of negative 5 is equal to 1 minus 5, which is negative 4. So in other words, the place where these two surfaces, well, one curve, one surface, but where this line and this plane intersect is the point 11 to negative 4. 11 to negative 4. Any questions about this? Okay. Okay, the last thing that we can do in terms of planes is we can restrict, if we have a plane, and we let's say, okay, I want y to be 0. How does this thing look? It will look like a line, right? So if I have a plane, here's my plane. And they tell us, let's say it's negative 2x plus 3y plus z, negative 2x plus 3y plus z is equal to 6. So I can say, okay, let's say I want to see how this thing looks if I take x equal to 0. So if x is 0, I'm on the zy plane, right? Because my x is 0. And what I'm going to get is I'm going to get this line right over here. Right? I mean, the plane keeps going, so it's not like at the edge of the plane, but it's some line. I did not draw the plane correctly, though, because as you can see, this line has a negative slope. So if I go to the zy direction, zy, then this line over here has, the way I drew it, some negative slope. But if I look at, oh, 1 second, z, oh, okay, no, it's fine, it's drawn. Okay, and you can keep doing this and find different lines. So you can set y equal to 0, you'll find a line, and z equal to 0, and you're gonna find another line. So that's the last part that they mentioned. So for example, yeah, so this line over here is the line when x is equal to 0. This line over here is the line where z is equal to 0. And you can graph these lines because they're just lines. And this line over here is the line when y is equal to 0. And actually, by graphing these different lines, you can try to figure out how your plane looks, and you can then graph your plane. So this is a good way, and we will see in general that in order to graph surfaces, it's easier sometimes to restrict yourself to different dimensions and see how these surfaces look. So we're basically going to stop here. Does anyone want, I have office hours now. Is anyone going to come? If so, let me know. Otherwise, Okay.